Humans and physics don't necessarily mix well when it comes to trauma. All right, so ultimately it's going to be our patient assessment that determines how the patient is and where they're going. Okay, but let's say you're dispatched to Route 84 for a patient that has been ejected and is now down in a ditch. Do you think you want to do anything proactively before you get there?
Call bird.
You want to see if the helicopter's available, okay? Because that might be very much needed, and you're going to have to go down in the ditch and get them. So it's going to take a little bit. So it has time for the helicopter to arrive, okay? But this has the potential of the patient being severely injured, okay? So if you get calls like that, think ahead and say, am I going to need the helicopter? You can always cancel it. There are places that it's auto-launched. I think in Orange County in certain calls it's auto-launched, right? Yeah. So you can always cancel it if you don't need it. Okay? So you can predict to some extent what injuries the patient may have. Okay? If the patient gets hit, T-boned in the driver's side door, what injuries are they going to have? Is it going to be to the left side of their body? Yes. Okay. It could be ribs, could be spleen, could be pelvis, lung, right? So it's not rocket science. You just think about, okay, where can they be injured because of how they crashed? Okay. Now, if somebody rolls or somebody spins, well, then it's a little harder to predict. Okay. All right. So energy and velocity and mass. Okay. So kinetic energy equals half the mass, but the volume squared. Okay. So energy doesn't get lost, but it can change its state. It's always there, just changes. Okay. It can be transformed into movement, heat, or deformation, meaning like the car. Our cars now have been designed to absorb impact. That's how they are now designed. Okay. So a lot of times the cars look terrible, but it is absorbed the impact so that the human in the car does not. Okay? So by the amount of damage, it's not always possible to tell how injured somebody is. All right, so it's obviously worse if the person is not restrained. Okay? But what happens when you hit something? The car stops.
You don't.
Right? And you don't until something stops you, right? Whether that be the steering wheel, the windshield, or the pavement if you get thrown out of the car, all right? Or if you're wearing a seatbelt, you get stopped against the seatbelt. What happens to your organs?
Squish.
They keep going until they hit the inside of your chest cavity, okay? So if it's a high-speed crash, you may get your aorta ripped from the ligament because of the amount of force. So those are the people that you get on scene and they're dead. Okay? And there's nothing you're going to do about that. So if you hit a stationary object, obviously the faster you're going, the worse it's going to be for you. Okay? Does that stationary object have energy? Yes, it does. Okay. What if you have a head-on collision and the other car is going 50 and you're going 60? That is going to be a pretty spectacular crash, right? Because you've got speed and energy coming from both directions. All right. So, Newton's first law of motion. Yes, you need to know these. A body at rest will remain at rest, and a body in motion will remain in motion unless acted upon by an outside force. Okay, so that outside force could be your seatbelt, it could be your steering wheel or your windshield, or it could be the pavement that stops you. Okay, it just depends on the situation. The second law, energy can neither be created nor destroyed, only changed in form. So, heat, noise, vehicle deformation, or tissue damage, or all of the above. What happens when you apply your brakes? Do they heat up? Sure, right? So that's the energy, it's heating up. And then the third law of motion. For every action, there is an equal and opposite reaction. So, there's not much left of that car. That's a small car. There's another car over there, upside down. So that was a pretty good crash. What would you expect their injuries to be? Could be. Could be. Okay, so it all depends on, number one, were they restrained? What are the safety features of the vehicle? Do they have airbags? Okay. And was there intrusion, and you can't really tell from this picture, into the passenger compartment? Okay. The vehicles are designed to avoid intrusion into the passenger compartment. One of the components of a patient being flown is there more than a foot of intrusion into the passenger compartment? Is there somebody that died in the same vehicle, right? Those are some of the criteria for flying the bird. All right, so your formula, again, is half the mass and twice the velocity. So, does the size of the object or the speed of the object make more impact on kinetic energy? Speed. Okay. All right. So, if you look at these examples here, look at the kinetic energy of somebody that's a 150-pound person. Okay, going 30 miles an hour. That's a lot of kinetic energy, right? So, I knew that was coming. Look at the difference, though. If you increase the mass by 10 pounds, you get 72,000 units, but if you take that same thing and increase it by 10 miles an hour, it's a much bigger difference. So speed, as the state troopers say, speed kills. All right. So, force. Mass times acceleration equals force. So stopping distance and time. So if someone was able to step on the brakes before they hit said pole, that's going to reduce the amount of energy from when they hit the pole, because it's going to slow down the speed. Okay? The shorter the stopping distance and time, the greater the energy exchange between objects. So that's when you slam on the brakes and the tires are, that's when you get your skid marks, right? Because it's a lot of force being applied and leaving rubber on the ground because the brakes and the tires are trying to stop and they're creating friction. Okay? So you're changing that energy into heat. All right, so if we think about these examples with body parts, organs in particular. The top example are organs that are hollow, okay? So, let's say it's a lung, let's say it's a gallbladder, irregular bladder, all that. That will be impacted a certain way, and if it breaks that, let's say, or your intestines, that's hollow, right? If it bursts, then whatever is in that organ goes into your abdominal cavity. Is that bad?
Mm-hmm.
Will that kill you right away? Probably not, okay? But you're probably going to get, like, hugely septic because poop is designed to stay in your intestines and not be anywhere else, right? Same thing with urine and anything like that. But then you have your solid organs, so like your spleen, your liver, okay? Those are the ones that bleed a lot when impacted by forces. okay? So that's basically what they're trying to say. So your organs that are not solid, they will deform and they may break, okay? The ones that are solid, they're gonna bleed. All right, so blunt trauma, if it's applied over a larger surface, it's gonna be maybe less, it won't go in as far because it's a bigger area, right? So maybe the organs underneath won't be as impacted. Penetrating trauma, it's a smaller area, but a lot of energy, so that can have a greater destructive force to that one area. So knives and bullets, right? Knives, less velocity, but it depends on the size of the blade, and where it is. If it hits something important, that's bad, right? So if somebody takes a 12-inch knife and like buries it in somebody's chest, you're probably going to hit something that's fairly important, okay? Whereas if somebody hits their chest on the steering wheel, it's a larger area. They may have some injury, depending on the amount of energy, but maybe they won't be as injured. It depends. All right, so gunshot wounds. There's a lot of variation depending on the type of weapon, the size of the bullet,